And we're back. Okay, chapter 4, applications of derivatives. So we're getting into what do we do with all these fun tricks that I taught you last chapter. So again, last chapter we learned how to take derivative. This chapter we're going to figure out why do we take a derivative. So looking here, I have just a nice little example here. So the textbook gives this example to start out. You have the mileage of a certain car can be approximated by m of v is equal to 0.00015 v cubed minus 0.032 v squared plus 1.8 v plus 1.7. At what speed should you drive to obtain the best gas mileage? So a couple things that we have to interpret from here. First off, the M stands for mileage. V, I think they're trying to say velocity here, but really we're talking about speed because you really don't want to measure the velocity on your car because it is a vector quantity. So from past classes, you know that one way to do this is to graph this and look for what we call the maximum value being the highest point on the graph. So if you look back here, I've actually given the graphing window to graph this. So pause this, probably plug this into Y1 on your calculator, and then use this as your window. And when you come back, I will show you on my calculator. So here's my calculator. Again, helps if I pull up my calculator. There we go. All right, cool. So I've plugged in the function into Y1. If I look at, let's see here. Nope, that was the wrong thing. Okay, 0.00015 x cubed. My window, again, I had that 0 to 100 and the 0 to 50. Those were the x min, x max, y min, y max for the graph. And now I can graph the function and I can see it looks roughly like this. So in the past, I imagine in like algebra 2 or so, when you were talking about the vertex of a parabola or like the max and min of a polynomial function, you learned that in the second trace menu, also known as the calculate menu, you have something called a maximum. There's also the minimum that you could have on there. So the maximum allows you to find the maximum value on a function. So here you can see it's laid out exactly like our zero finder. It asks for the left bound. So we just want to put this little cursor to the left of the maximum point. And we can see the maximum point is right where my cursor is right here. So I put my left bound, now right bound, go to the right of that maximum value. And guess, you can guess if you want to, I don't. So we can see that this function achieves a maximum of 32.128 at 38.602. Again, we have to go back into the setup problem. Sorry, I can't speak right now. To figure out what those stand for. So again, our independent variable here is the speed that the car is going. Our dependent variable is the mileage that we get off of that car. So again, looking back here, our independent variable says that we should be going 38.603 miles per hour to get the best mileage on this car. And the best mileage that we can get on this car is going to be at a, right here. Our best mileage of this car is going to be at 32.128 miles per gallon. All right. So this chapter, you're going to figure out how to find that without the calculator. So the idea behind this chapter is being able to do it without the calculator. So before we get there, page 10. There we go. I have to give you some vocabulary. So definition of an absolute or global extreme value. If you let f be a function with domain D, then f of c is the absolute maximum value on D if and only if f of x is less than or equal to c for all x in D. It is the absolute minimum value on D if and only if f of x is greater than or equal to f of c for all x in D. If and only if f of x is greater than or equal to f of c for all x on the domain. These look like really complicated ways of saying things, and they are. They're complicated ways of saying really, really easy things. So looking at the definition of an absolute maximum value. Absolute maximum just means if I have some sort of function right here, looking right there, I think you can figure out that this is your maximum value, right? Just by looking at it. It occurs at the point C. Just like I was trying to show you guys last chapter, the location is the x value. What it is the f value, so f of c here. So you can see that all of the points on the function are below f of c, making f of c our absolute or our global max. So those are certain things that you have to commit to memory. Absolute global means it's the highest for the entire domain of the function. Versus if I'm talking about absolute min, again, we've got our weird way of saying it over here. Let's just say I have a function that looks like this. You can see that that function has a minimum value right here. The location of that minimum value is c, and the value of it is f of c. Again, this is an absolute or global min. Remembering absolute or global means the smallest of all of the things. All right? So what I have for you now is just different ways that absolute extrema can occur. All of these functions down here are all functions, they're all dealing with the function y equals x squared. And you know what the function y equals x squared looks like. It's a parabola. It's the most basic parabola that you could think of. The domain of y equals x squared is all reals. It goes from negative infinity to infinity. If I look at the graph of that function, the graph of that function will have an absolute minimum, but it does not have an absolute maximum because it goes up. Some people in the past have had difficulty with understanding that this function does not have an absolute maximum because it goes up to the highest value. Here's where you have to be aware, infinity is not a number. So because this function goes up to infinity, it does not have a maximum value, but its minimum is 0 and it occurs at x equals 0. So again, unrestricted domain in this case has an absolute min, does not have an absolute max. So I guess what we're trying to get at here is there's no guarantee that you're going to have an absolute value, period. If I change this to a closed domain where I have the two endpoints are inclusive, where I can get to 0 and get to 2, because I have this closed domain, I now have an absolute maximum. This function, because I limited the domain, again, remember the definitions from the previous page indicated that for a value to be an absolute maximum, the values on the domain of the function have to all be smaller than it. So look in here, I can achieve my absolute maximum, I can achieve my absolute minimum if I have this closed interval. Now, if I change one of those endpoints, let's say I go down here and change my endpoint to exclusive at 0. Exclusive at 0 means I have an open circle at 0. That means as I approach the x value of 0, I get infinitely close to it, but I never quite reach it. So in this case, where I have this open domain, I have no minimum. Those open circles will not be minimum values. And just because I wanted to toss it in there, let's say I make both endpoints open. If both endpoints are open, then there's no minimum, no maximum, because again, those are open circles. But really what we wanted to focus on here is the only guarantee that I had for a minimum and a maximum was if we had a closed domain, all right? And it'd be really nice if we could bundle that up as a theorem. Maybe we could call it the extreme value theorem. There we go, that's it. If f is continuous over a closed interval, then f has a maximum and a minimum value over that interval. So that's something that you have to acknowledge. If the function is continuous and you have a closed interval, then f has a maximum and a minimum value over that interval. So looking back up here, the only closed interval was this second one. The unrestricted domain, open interval. 0 to 2, with 0 being exclusive, open interval. Open interval on 0 to 2 with both endpoints being exclusive. Only the closed interval where I have or equal to at 0 and or equal to at 2. Closed circles means guaranteed minimum and maximum. So that is the extreme value theorem. If f is continuous over a closed interval, then f has a maximum and a minimum over that interval. Maximum and minimum values can occur at interior points or at endpoints or at a mixture of the interior and endpoints. And just to be clear, I think that just looking visually where maxima and minima are, there's your max value, there's your min value. Maximum, minimum, minimum, maximum. Again, visually, they're really easy to recognize. Whew. Local extreme values, instead of the absolute or global extreme values, local extreme values are within like a local neighborhood. So a local maximum is the maximum value within some open interval. A local minimum is the minimum within some open interval. Now, keep in mind, since we're talking about an open interval, you're not guaranteed to have local extrema, but you could have them. They can occur. You're just not guaranteed to have them. So there's a difference between the extreme value and us looking for the local extremes. So I have a picture here for you, and you can actually see where you have minima and maxima. So just like running through these, I can see that this is a minimum value, right? Since it's the minimum over the entire function, it is the absolute minimum. Any absolute minimum is also going to be a local minimum, also known as a relative minimum. So looking here, this is both the absolute minimum and a local minimum. Now if I look over here, this right here is the smallest value for its local neighborhood. I mean, it dips down and that's a minimum value. So that's just a straightforward local minimum. So note the difference between the local minimum and the absolute minimum. The local minimum is still higher than the absolute minimum, but it is smallest for those around it. I'll point out there's one other local minimum here. Looking right here, that is another local minimum. Again, minima and maxima can occur at endpoints, or they can occur at interior points. Now looking here, this is a local maximum. This is also a local maximum, but since it's the highest of all of the local maxima, it is known as the absolute or the global maximum. Now, if you look at those interior, the interior local extrema, those local minima, local maxima, what we have here is something that we were trying to train ourselves to look for last chapter. I realized I was trying to illustrate something with my pen, and you guys couldn't see my pen. So looking here, see how we have like a horizontal tangent right there? A horizontal tangent right there? And we have no tangent right here because we have a cuspy kind of thing. So what we have to recognize here, where local extrema occur, are where the derivative is either equal to 0 or undefined. That's a very important thing to recognize. So important that we use that to define our local extreme values. So if a function f has a local minimum value or a local maximum value or a local minimum value at an interior point C of its domain, and if f prime exists at C, then f prime of C is equal to 0. We define critical points as a point in the domain of a function f at which f prime is equal to 0 or f prime does not exist. Maximum and minimum points in the interior of a function always occur at critical points, but critical points are not always maxima or minima. I cannot stress how important, I cannot stress enough how important it is to know what a critical point is. For this chapter, you will be finding critical points at the start of every single problem, just about. And a critical point, again, is where the derivative is 0 or it does not exist. And we'll get more into that in just a second. Heck, let's do it right now. So find absolute maximum and minimum values of f of x equals 3x to the 2/3 power on the interval between -1 and 2. So again, we have to start by finding our critical points. And again, I'm going to point out over here that we got two strategies. We got graphical and analytical. The graphical one's going to be really easy. So we're going to save that for after we do it the cool way. And the cool way is going to be using calculus. So again, first thing we have to do is find the critical point. Critical point is where the derivative is equal to 0 or undefined. So what you need to do right now is calculate the derivative of this function. So maybe pause this screen, calculate the derivative. And like I said, you should be calculating the derivative. So we have f prime of x is equal to, looking up here, 3 is a constant multiple. I've got 3 times, bring your exponent down, so 3 times 2/3, x to the 2/3 minus 1. So just real quickly here, crossy, we've got 2x to the -1/3 power. And last chapter I told you that you didn't have to simplify anything. Now here's where you want to write everything as a singular fraction with positive exponents. So we're going to call this 2 over x to the 1/3 power. And the reason we do that is so that we can find our critical points really easily. Our critical points exist where the derivative is either 0 or undefined. So to find our critical points, the first thing that we do to make a fraction into 0 is set your numerator equal to 0. We look up here. In this case, that's saying 2 equals 0. For what values of x does 2 equal 0? Okay, that's a null set. There's no critical points from your numerator here. The second type of critical point is where your derivative does not exist. And a derivative is not going to exist when the denominator of it is 0. So we set our denominator. Equal to 0. And looking at that, now I see I've got x to the 1/3 power is equal to 0. That means x equals 0 is my one critical point in this situation. Now what I have to figure out, is that a maximum, is it a minimum, or is it neither? Now keep in mind, because I have this closed interval from -1 to 2, inclusive of the two endpoints, I am guaranteed to have a maximum and to have a minimum. The only way to figure out what is our maxima and what is our minima is to use a table of values. And that table of values is going to be just listing our candidates of our maxima and minima and figuring out, is it the highest or the lowest? So our candidates for this are going to be x equals 0. There's two other candidates. See if you can determine what those two other candidates are. Those two other candidates are the endpoints of the interval. This is something big that people, when they're taking the AP test, generally tend to miss. They forget that it is possible to have your endpoints be your maxima or minimum. So now we've got our x values. All we have to do now is determine what our function values are. And our function values are just going to be like -1 to the 2/3 power. Okay, -1 squared is 1, cube root of 1, that's 1. Our function value here is going to be 0 to the 2/3 power, which is just going to be 0. Then over here for 2, we're going to have 2 to the 2/3 power. So 2 to the 2/3 power, well, that's just going to be the cube root of 4. One of those is the absolute biggest, one of those is the absolute smallest. To figure out which one's the biggest, look at these 3 values. 1, 0, and cube root of 4. Which one's the biggest? And it occurs at x equals 2. We have a min of 0, and it occurs at x equals 0. So it's important to keep in mind which one is the minimum, which one is the maximum, and by which one is the minimum, which one is the maximum, I'm referring to the x or the function value. Our max is the cube root of 4. It occurs at x equals 2. Now the other way that we can do this, again, we can just bust out our calculator, and looking at that, we plug in the original function here. So our original function was, what was it? 3x to the 2/3 power. So 3x to the 2/3 power. What I like to do here is restrict my viewing window. Again, I know that I'm talking about between -1 and 2. So I'm going to make my x min -1, my x max 2, maybe count by ones. Over here, my y min, just because I did my work, I know that my y min should be 0, but let's make it like -2. Let's make our y max 5. Count by 1, count by ones, I said. And you graph it, you're actually able to literally see the minimum value is 0. It occurs at 0. Your maximum value, you can't really see it, but you can see that it happens at the endpoint. It goes up and becomes biggestest at the endpoint. All right. Here's another problem. I will point out that it just says find the extreme values. It does not say find the absolute extreme values. So we're looking both for the absolute and the local extrema on this problem. The first thing that we need to do is identify our, actually, on this problem, it's a little bit different. We have to identify our domain in this problem. So identifying our domain, we actually look, we've got a fraction here. We know that the domain cannot have 0, or the function cannot have 0 in the denominator. We see that plugging in either 3 or -3 is going to yield a 0 in the denominator because I got 9 minus x squared. Even further, if I plug in anything bigger than 3 or more negative than -3, I'm going to yield a negative underneath my radical, which is going to introduce imaginary numbers. So looking at this problem, the domain of my function is -3 to 3 with open endpoints. So here, I'm not guaranteed to have a minimum. I'm not guaranteed to have a minimum. I'm not guaranteed to have a maximum. So now I need to proceed with some caution. We remember from last chapter that if I'm trying to find the derivative of the square root of 9 minus 1 over the square root of 9 minus x squared, I have to look at this as 9 minus x squared to the -1/2 power. So now I can have f prime of x is equal to, outermost function is that -1/2 power, so this would be -1/2 quantity 9 minus x squared to the -1/2 minus 1 times the derivative of the inside. And the derivative of the inside, I got 9 minus x squared, so 9 goes away. I have -2x here. Again, last chapter, you did not have to simplify. This chapter, your life is going to be much easier if you do simplify. I got negative, I got negative. Those cancel off. I got 2, I got 2. So I know everything about the -1/2 and the -2 go bye-bye. I know here I've got a -3/2 power. So x is the only thing in the numerator, and 9 minus x squared to the 3/2 power in the denominator. To find my critical points, again, my critical points are my candidates for my maximum and my minimum. My critical points, I have to set my numerator equal to 0 and set my denominator equal to 0. So one critical point is where my numerator equals 0, x equals 0. Good, there's one critical point. My other critical points occur when 9 minus x squared to the 3/2 power is equal to 0. Well, I can raise both sides to the 2/3 power. I end up with 9 minus x squared is equal to 0. Add x squared to both sides, I've got 9 equals x squared. Square root, I've got x is equal to plus or minus 3. Oh crap, those are not points on the function. So those are not going to be possible minima or maxima. So really, since those are not in the domain, they are not critical points. I have only one critical point. That means I'm only going to have, well, at most, I'm going to have either a minimum or a maximum. It is also possible that this guy right here, the x equals 0, is neither a minimum nor a maximum. So to explore that, again, the only tool you guys have in your wheelhouse is what we call a table of values. So looking here, I've got 0 and f of x. Again, I'm just using the function values to explore this. So I've got 0 plugged into f of x. Well, looking up here, that's just going to be 1 minus 1 over, the square root of 9 minus 1 squared, which would be 1 over the square root of it. No. Let's back up here a little bit. Apparently I can't plug in too well. I apologize for that one. It's going to be 1 over 9 minus 0 squared, which would be 1 over square root of 9, 1/3. The problem is I don't know if that's bigger or smaller than the points around it. In order to find out if it is bigger or smaller, what I have to do is find comparison points. Now remember, when we set up the domain, I'm going to put these in red because I know -3 is not possible to be in this function and 3 is not possible to be in this function. I know that those function values are non-existent. So in order to find out if 1/3 is the highest or lowest in its local neighborhood, I just need to find out some point between 0 and -3. And just for ease purposes here, I'm going to call it -1 and 1. So let's just give me some comparison values for the critical point here. Now looking at this, if I plug in -1 into the original function, here's where I'm going to have 1 over the square root of 9 minus -1 squared, which would be 1 over the square root of 8. Over here, I'm also going to have 1 over the square root of 9 minus 1 squared, which would still be 1 over the square root of 8. Now looking to see if 1 over the square root of 8 is bigger or smaller than 1/3. I could use a calculator to approximate what the 1 over square root of 8 is, but my whole goal here is to not use a calculator. So I see the square root of 8 is smaller than the square root of 9. Since my denominator is smaller, this has become bigger. So this is going to be greater. This is going to be greater. This ends up being a minimum value. We have a minimum value of 1/3 and it occurs at 0. Min of 1/3 at x equals 0. There's all my extreme values. And again, I wanted to do this without using my calculator. Now I can grab my calculator and see if it makes sense there. So turn on my calculator. In my y equals menu, I can type in my function, 1 over the square root of 9 minus x squared. I'm just going to use the standard zoom window. And I can physically see that the lowest point here is right where my cursor is. And to find out what that value is, I can go to my min, left bound, right bound, and nobody guesses, but I'm going to guess anyway. So I can see that my minimum, well, the calculator alleges that it's negative 4.121 times 10 to the negative 6th. That's 0. And it has a value of 1/3. So again, it just feels cooler to be able to do that without touching my calculator. If you don't like using the table of values for this, it seems kind of wishy-washy, especially considering like we had to guess to find that -1 and 1. There are other ways to determine whether 0 is a local min or a local max, and we'll be going over that. It's called the my favorite method of doing this is called the first derivative test. It just works so much better for me. But for now, you just have the function test where you have to find some test values nearby. And I said advance and advance. All right, cool. So finding maxima and minima analytically to find the derivative of the function and determine where the derivative is 0 or undefined. That's where we set the numerator equal to 0 and the denominator equal to 0. Those are called the critical points. Find the value of the function at each critical point. Find values or slopes for points between the critical points to determine if the critical points are the maxima or minima. For closed intervals, make sure you check the endpoints as well. Now there is something in here where I say find slopes for points between. That's using the first derivative test. You're not doing that right now. You're finding values between the critical points to determine whether you have a maximum or a minimum. All right? And I do want to point out here, again, critical points are not always extrema. So looking here, you can actually see this is y equals x cubed, the graph of y equals x cubed. If I follow the steps from before, I've got y prime is equal to 3x squared. I set my numerator equal to 0. I set my denominator equal to 0. So I say 3x squared equals 0 yields x equals 0. My denominator of 1 equals 0. That yields no critical points. So I see I have a critical point at x equals 0. Again, you have to check your values around that point to make sure that it is actually an extreme value. So here I'm talking about at 0, I find some local points around 0, and it's between 0 and whatever other critical point I have. So since there's no other critical point, I can literally use any negative number here. -1 is going to be the easiest. I look at f of x from there. F of x is going to be -1 cubed, which is -1. Looking at f of 0, that's 0 cubed, or 0. Choosing a point to the right of 0, that's 1. So I take 1 and cube it. That gives me 1. I look at my value right here. Is it bigger than or smaller than all of the numbers that are surrounding it? Well, one number is smaller than it. One number is bigger than it. So it is neither a maximum nor a minimum. The same would happen on this vertical tangent problem right here. I don't need a text box. I would again get a critical point where that vertical tangent exists at 0, but it is not a minimum or a maximum. So always investigate. And here are the suggested problems. We will, of course, be doing some of them in class tomorrow. I will see you tomorrow.